Today we're going to be talking about a new heat equation, which I like to call the delta H equation. This is going to be on page 14 of your packet, and you may or may not have to pause this video as we go through to get some of the information down, because I'm going to go through kind of quickly. So delta H equation, there's kind of two versions of it. The first is delta H equals moles times delta H FUS, which stands for heat of fusion. We'll get to that in a few minutes. Or you can use delta H equals moles times delta H of vaporization. VAP stands for vaporization, and again, we'll talk a little bit about what that means. So this equation, you'll notice it uses moles instead of mass. When we were using Q equals MC delta T, M stood for grams or mass, but here we're using moles. So just something to keep a track of. So the heat of fusion can be used for melting or freezing, and we use the delta H of fusion to go ahead and represent that. So heat of fusion is just essentially the heat needed to freeze or melt 1 mole of a substance. The units for that are going to be kilojoules per mole. Now, again, something we want to be really mindful of is with the delta H equation, we're using kilojoules per mole. However, when we did our Q equals MC delta T, we were using joules per gram degree Celsius. So something that we really need to be mindful of is making sure we have our units in kilojoules for delta H, but our units in joules for Q equals MC delta T. Then we have our heat of vaporization, which is used in the event of boiling or condensation of a substance. And we use delta H VAP to represent that in the equation. And this represents the amount of energy needed to change 1 mole of a substance from liquid to gas, or vice versa. So we could also go from gas to liquid. That would be condensation. And again, our units are kilojoules per mole. So on to an example. In this case, it says how much energy is required to melt 147 grams of ice at its melting point. A couple of important pieces of information in this question. First, we're solving for energy, because it asks us how much energy. So we're solving for delta H, and that's just regular delta H, not with the little FUS at the end of it, just delta H. It's telling us that we have 147 grams of ice. Again, we have to be careful with the fact that it says grams. We can use this information to help us convert to moles later. Then it tells us that this is happening at the melting point. Something that this tells us, number one, is that there's no temperature change. That's how we know we're not using Q equals MC delta T anymore, because we don't have a delta T. When you're having a phase change, that temperature is going to be constant, so no delta T is needed. The other thing that this tells us is that we are going to be using our delta H of fusion, because fusion is used for melting or for freezing. So we're going to just cross off the whole delta H of vaporization number, because we don't need it for this problem. So the next easiest thing to do is just write out your variables. Delta H is again what we're solving for. Moles, we're given grams, and our delta H of fusion is given to us in the problem. We just had to identify that that was the thing that we needed to use. So in order to solve for delta H, what I'm going to do is start out with my grams. I'm going to just put this all into one equation so that I can do this as simply as possible. And I know that I can convert from grams to moles by dividing by my molar mass. So I put 18.02 grams of H2O on the bottom, H2O being the molar mass of water, and 1 mole of water goes on top. Then I can do something a little bit different than I've done in the past. I know that if I'm going to continue doing a stoichiometric dimensional analysis or a unit conversion problem, that 1 mole of H2O would have to go on the bottom. Now the question is, what goes on top? Well, we're left with this delta H of fusion constant. So what we can do is we can take 6.02 kilojoules and put that on top. So we've now canceled out grams, we've canceled out moles, and we're left with kilojoules. And that should make sense because our answer is, we're looking for delta H, and delta H is just the change in heat, which we're going to measure in kilojoules. So the math, 884.94 if you multiply everything on top, and then everything on the bottom, 18.02, you go ahead and divide, and you end up with this value in your calculator, 49.10876, yada, yada, yada. With that, you're allowed 3 significant figures because of the 147. We don't use the delta H of fusion or the delta H of vaporization for our significant figures because those aren't measurements that we would make. Those are measurements that were made by scientists and agreed upon, so we don't use that to limit our significant figures. So I drew my little line after 3 significant figures. So my final answer becomes 49.1 kilojoules. One last example before I let you start in on your homework. This one says, how many moles of oxygen gas are present if 29.7 kilojoules of energy are required to evaporate the sample? So again, moles is what we're solving for. It tells us that 29.7 kilojoules of energy are required to evaporate the sample. Evaporation is really similar to boiling, where we're going from the liquid phase to the gaseous phase. So what that tells us is we are going to be using our delta H of vaporization. And the easiest thing to do is just go ahead and plug in the information that we know. Delta H is the energy, 29.7. We're solving for moles, and our delta H of vaporization is given to us 6.82 kilojoules per mole. So now we're going to go ahead and plug into our equation. We don't necessarily have to do everything stoichiometrically. We can just solve the equation the way that it's written. So here's our equation, delta H equals moles times delta H of vaporization. And then we can plug in our 29.7 kilojoules for delta H. We can plug in our 6.82, and then we would divide away 6.82 on both sides to isolate the moles just on the right side. So then what we're left with, 29.7 divided by 6.82, we are left with 4.35 moles of oxygen. So good luck on your homework. A couple of tips for you before you get started. With number 1, 83 was crossed off as the correct answer. 84 was written in. It's also definitely possible to get 83. It kind of depends a little bit on where you round. So if you get 83 or you get 84, that's okay. Another common mistake is writing the formula for carbon tetrachloride. Just remember, what does tetra stand for? Does it stand for 3? Does it stand for 4? Remember your rules for naming covalent compounds. And then another thing is that you have to remember how to name or write the formulas for Hunkelbreff elements. And then number 5 is a question that you have to do. It's not optional. It says write and solve your own delta H equation. So a couple of things. You can research a delta H fusion or a delta H vaporization constant, and you would just come up with your own mass and your own delta H. If you want an extra credit point, you can add a storyline to your question, and you can get 1 point of extra credit. So best of luck. If you have any questions, feel free to send me an email, and have a good one.